Well, good afternoon, and thank you for joining us for our talk, and thanks to Black Hat for asking us to be here in the first place. We'd like to spend a little bit of time sharing with you some of the work we've been doing creating synthetic persons for cyberspace operations. Disclaimer, this is more of an in-progress review than it is a product release. So our intent is to show you our work, warts and all, and maybe start a conversation. So please be, ask prodding questions. We love those. After all, we're Sortech, the company at which we work, is in the business of research and development with emphasis on research. So we all know how that pans out. My role in the company is I'm a lead scientist. I'm Fernando Maimi, and Alex is one of our top engineers.
I'm Alex Nichols. I'm the technical director for cyberspace operations at Sortech. I've been with the company about 6.5 years or so. I have a bachelor's degree in computer science.
And I've been with the company for a couple of years. Before that, I was in the Army for 25 years in the US Army, doing cyberspace operations for a good chunk of that. And then afterwards, I stayed around for 2 years as a civilian to stand up the Army's new think tank on cyberspace issues, and then decided it was enough to think about big things and it was time to start building some stuff. So I joined Sortech. Today, what we'd like to do with you is first start off with a really brief introduction to artificial intelligence, just to get our terminology correct, because there's a whole bunch of hype around it, and I want to make sure we set the basis on that. And then afterwards, we're going to talk about some threats that we have identified in and around the space of in and around the intersection of AI and cyberspace. And then we're going to get into the good stuff, which is the 3 agents that we have built, and then hopefully start a conversation about what lies ahead. So with that, you ask 10 different people what artificial intelligence is, and you're likely to get 10 different answers. So basically, firstly, don't get angry at me if your favorite flavor of artificial intelligence isn't here. Don't throw rocks at me or anything. It's just that you can only go so far before the font gets tiny and nobody can read it anyway. But what I want you to get out of this slide is that there's really 2 basic branches, or 2 main branches to the artificial intelligence field, which is huge. On the right-hand side, we have the symbolic approaches, which are if you think back to the 1980s and expert systems, and that's what they were and that's what they've grown up to be. And that includes some cognitive architectures, which are shown in here. I'm highlighting SOAR because that's the one we happen to build our agents on, but there's another famous one, which is ACTAR. ACTAR is promoted by the Carnegie Mellon University, and SOAR is out of the University of Michigan. Both are open source cognitive architectures. These systems think in terms that humans can relate to, using constructs that humans can relate to. On the left-hand side of the tree, of the family tree, are the non-symbolic approaches, which is it's all the rave in the news, right? That's where neural networks are, where hidden Markov models are, LSTMs. We've heard other talks using some of these technologies. So the left-hand side is really good at finding, doing 3 things really. It's classification, clustering, and predictive analytics. That's if you can distill the problem to those essence, it goes on the left side. If it's more complicated and it requires some knowledge engineering, it typically falls on the right side. So what does that left side look like? Essentially, every non-symbolic approach looks something like this, and you can omit some pieces. What I want to key in here is that the hard part about building non-symbolic or machine learning systems is in identifying what the features are that you're going to go after. And some people just throw everything in there, but it's better to be deliberate about it, and then choose your algorithm correctly. And thankfully, we have things like cars and other platforms that allow us, where people have built these libraries of LSTMs and other algorithms, so the developer's job is a lot easier. And in this case, the bane of non-symbolic learning or non-symbolic machine learning is that you need large sets of data to train the system and say yay or nay. And we can play with that number, but sometimes it's in the thousands, sometimes in the millions of samples before we get some good results. On the other side of the family, we have symbolic approaches. What I'm showing here in this, as Alex calls it, garish chart, is my attempt at visualizing what SOAR looks like on the inside. The magic happens in the middle. That's the working memory representation, and that's a part of the agent that thinks kind of like our executive, processes in the brain do. There are 3 pieces of important memory that we're going to touch on later. On the far left is procedural memory. Think of this as how to do things, how to put together a peanut butter and jelly sandwich, how to scan a network, whatever that looks like. Then we have semantic memory, which identifies how things are related to each other in the real world. Think of it as an ontology or declarative knowledge. And then episodic memory is where the agent, as it experiences the world, remembers how it dealt with specific problems, and it actually learns from those experiences and improves its performance over time. And then at the bottom, you have output links, so you can send commands out to a motor or whatever, if it's a robot or some tool in the cyber world. And then it has on the far left some input links where it takes feedback from the space. So way different than non-symbolic approaches, and this is what we base a lot of our work that we're going to share with you today on. But before we do that, let's talk briefly about some of the threats that we discovered that we're concerned about, we're tracking. 2 years ago, I was fortunate enough to be part of a task force that the Army stood up to identify what the battlefield of 2050 was going to look like. And these are some of the key takeaways we came out with. The full report is available for free at the Army Research Lab website, but these are the ones that stuck with me anyway. And I want you to remember that the middle one, almost middle one, the fourth one down, micro-targeting, because that gets after very, very deliberate, very targeted spear phishing attacks. And this is something we're already seeing in the wild. And also the last two items are really what get to the key motivation for the work that we have done, is the realization that autonomy is going to play a key role out in cyberspace, and that cognitive models of adversaries and friendly forces too is very important. So that is what the future looks like. I want to bring it back to the here and now. And there's a lot of hype about AI-powered cyber attacks. The reality is a little more nuanced. We haven't seen an awful lot of effective applications of it in the wild. These are just some examples that I pulled up. A deep exploit was down in the arsenal earlier. It was originally released, I believe, at Black Hat US this past summer, but he's down there today briefing. And then SnapR, which unfortunately hasn't seen very many updates that I can see, at least on GitHub, in the last couple of years, is all about that micro-targeting I talked about. So the idea here is they're using machine learning to analyze a target's Twitter feed and then craft messages that have a high likelihood of generating a click from that user and then hopefully an infection. So it's all early stage, but if you do the math and you extrapolate from that very first slide I showed, from the previous slide to this one, and you can see where the trends are pointing in a clear direction. But even if it's not adversarial, AI is not perfect. So there's a whole bunch of things we should be concerned about whenever we think about AI in the context of cybersecurity. On the far left is probably my favorite. Anybody get to play with Microsoft Tide before they shut it down? No? It was up for 16 glorious minutes in 2016 before some very creative folks decided to teach it how to behave rudely online, and Microsoft pulled the plug. So what happened there was it was designed to learn by interacting with humans, and those humans turned out to be, well, fiendish, I guess. So that's an example of what happens when real AI systems interact with the real world. In the middle, I think some of you may have heard of the MIT experiments where they put pieces of duct tape on stop signs to fool the vision systems on vehicles so they wouldn't recognize it as a stop sign and cause an accident. Right, nefarious, but hey, some folks at the University of Japan came up with a way to do the same thing essentially with a 1 pixel modification on the image. And you can see the different classification between what it was supposed to be recognized as or classified as and what actually ended up getting classified as. And on the far right, even in the absence of these things, there's bias that we all introduce into the systems we build, and a lot of times don't even realize that we're doing that. So here we have an example of Google getting in trouble in 2016 over something that just was representative of what people were Googling for. If somebody Googled for three black teens, they got pictures of teenagers in prison, and white teens on the right side, well, enjoying life. Not deliberate, there was no malice behind it, it was just a byproduct of biases in the data sets. So with this environment, let's get to the meat of it and how cyber cognitive agents or CyCog agents might fit into this. What we were looking for was agents that can act in cyberspace and do complicated tasks, not just very narrow applications that we see in machine learning a lot of times. To us, in order to be classified as an autonomous agent, the entity has to be able to do 4 things. It has to sense the environment, think about the environment and its goals and what it should do about it, and then act on it. And over time, the fourth one is to learn about it. We applied this in 3 different spaces for different applications and different customers. The first one was somebody came to us and asked us to build an autonomous agent that could behave as a red team member, or more accurately, a penetration tester. And we did that, but what we discovered along the way was this was way better at adversarial emulation than it was at pen testing for a bunch of reasons that I really don't have time to get into right now, unless you ask questions afterwards. But it was very good at that job. Then somebody else came out afterwards and asked us, hey, can you use a similar approach to building autonomous defenders? And we said, sure, we can try it. And along the way, we discovered that there was enough similarities between the two that we should start extracting some of the code base, because as Alex is going to point out here shortly, writing SOAR code is not fun by a long shot. So we developed this family tree, and then when DARPA came to us last year, and I said, can you do something like that, but model regular users so we can do human vulnerability assessment? We said, sure, and that's where the third the child in the family came up, which is CyCog-U. My apologies ahead of time. CyCog-D we can't talk an awful lot about because of contractual reasons, but we are going to touch on it briefly here in a couple of slides. With that, let's dig into what CyCog-A looks like. And again, the idea was to be a penetration tester, and then we kind of morphed that into being an adversary emulation system, which is really, I think, where it shines. But at the heart of this was the notion of we had to teach the agent tactics, techniques, and procedures that were realistic and representative of some adversary in the real world. And that's, quite honestly, that's the first wart I'm going to pull out, because when you're dealing with symbolic artificial intelligence, that means you have to do all the knowledge engineering by hand ahead of time, which means somebody has to code all these behaviors in there. Not so much with machine learning, but you can get this complexity, this richness of behaviors using strictly machine learning. So that was our first stumbling block. But before I get ahead of myself here, let me hand it over to Alex, and he can walk you through the architecture of the system.
All right, so this is our CyCog architecture. Most of these components we're going to go into in a lot of detail in a few minutes, so I'm going to skip over most of them. The takeaways from this slide are this works as a single VM, so all the components you need to run this agent are in a single virtual machine that you can then drop into whatever environment it is you want to test. So this big box is one self-contained VM full of all of your fun tools. At the top you have an agent and an abstraction layer so it can interface with tools. The tools themselves I'll get into in heavy detail in a minute. On the bottom are other things living on the machine. There's the C4 server. This is our command and control server, so we can do fun things like start and stop the agents and tell them to, hey, go work over here, or don't touch that thing, or hey, just hold up for a minute, things like that. It's controlled right now over IRC, actually, so you can use a standard IRC chat client to give it instructions and tell it what to do. You'll also see down there TTP models and an asset DB box. We'll get into the TTP models again later, but that's the instructions that tell it how to act as different people in cyberspace. And then the asset DB in the corner is where we store all of the stuff we need to know about cyberspace. It turns out this is a hard problem. If you want your agents to be able to act in different ways with different assets in cyberspace, you need to record it somehow, and that can be challenging at times. So for example, if I discover a host out in cyberspace, I need to record that that host exists. There is a physical network adapter attached to it. That physical adapter corresponds to a logical adapter somewhere. That logical adapter has multiple forms of ways it can be addressed. All of those things get stored in that asset database. This is a screenshot of our attacker agent.
Don't hate us. We are not user experience experts. I know it can be prettier.
At the top, you have a task breakdown. So this is a task tree. It shows all of the different tasks and goals an agent is trying to break apart and use to move around in cyberspace. We have a blown-up version of this in a minute. I see a bunch of you in the back squinting at it. On the left, you can see a little IRC built in the client, so you can control it from the web interface. At the bottom, this piece is kind of cool. It's a console. It's an amalgamation of all of the different console windows that CyCog is currently using. So if it's running Nmap and a ping over here and SQL maps somewhere else, all of those consoles get pushed together, and you can actually see what the agent is typing and what the results of its commands are as it goes. This is a similar screenshot of our Defender agent. Most of it's similar, except this bottom panel changed. You can see there's these little tabs up here, so we have different visualization widgets you can drop in. This particular widget is a timeline. It shows the different things that the agent has responded to and the different things it's done. So something shows up on its alert feed response, it groks that and adds a firewall rule to deal with it. And then to the right of that, you have the alert feed response. So this is just an open source intelligence, threat intelligence feed. All right, so this is a breakdown of one of those task trees I showed you at the beginning. This is the secret sauce of what makes our agents smart and what they are. Real quick, so we can talk about this in the same terms, I'm going to show you what this is. This lives at the bottom of a phishing attack. So if the agent decides that it wants to phish a adversary somehow, it will propose this goal that says, use phishing injection method. And then from there, it starts to decompose it into different subtasks it needs to do to accomplish it. So over here, you see it selects, it has to pick how it's going to deliver the malware through the phishing. It picks that it's going to use a web link as opposed to sending an attachment or something like that. From there, it assembles a payload, puts a download at the end of where that link is going to be. And then it says, we have this phish with content goal. When you get to this goal, what it's doing essentially is it's saying, hey, now I need to assemble an email. So I need a from user, I need a target user, I need to build the body and the subject line of the email. And then you see a little blue dot here in the corner. That is the agent actually sending the email. You'll notice all these are green. This is because these goals have all succeeded. If you look over here, you can see some of the goals are yellow because they're in progress, and occasionally you'll also get red goals, which we'll get into in a minute. Those are failed goals, and they're very important for the system to work as well as it does. All right, this is our breakdown. This is the breakdown of our knowledge base. So this is all of the different goals and goals that the agent can work towards. You can think of this like a class definition, much as you would think of this as a class instantiation. It's worth noting that the overall knowledge base is a graph of goals that can be used to accomplish each other, whereas this is a tree of goals that have been used to accomplish each other. So even if I send 100 phishing emails, if I have an attack that's going to send 100 phishing emails, you're only going to find a send email goal in here one time. The beauty of this representation is what I'd like to call the critical mass effect. So as we add more and more goals and activities to this hierarchy, adding new ones gets easier and easier. So for example, if I want to add a goal in to allow myself to phish with an email attachment instead of a web link, I don't have to replace this whole structure. All I need to do is add in a new goal that says, hey, phish with an email attachment, and then I'll have to add something over here to actually assemble a payload that goes with an email. But I don't have to reteach the agent how to send emails or how to build them or what the content should look like. I just have to say, hey, here's one, let's swap out one piece of this, and then it can choose to do that instead of choosing what it's chosen in this example. This is zoomed in on that goal model. The guy who built this name is Randy Jones, for those of you who are curious why it says rage in lovely red flaming letters in the corner. So it's Randy's goal editor. This goes at the end of a SQL injection attack. So this is saying, hey, I want to do SQL injection. I need to find a host that I can do SQL injection on. So it proposes this identify target host goal. Then it will propose this goal for identifying target hosts. It will actually do some kind of scan on the network and find hosts that are running HTTP services. From there, it will crawl the HTTP services being hosted, gathering up URLs. And then it will take a look at those URLs, looking for URLs that have parameters that could possibly be used for injection. If all these goals work, at the end, the agent will record in its memory that, hey, I know of this host, here's this URL that can be injected upon, and I'm done. And all these goals will be marked as complete, and the agent can move on with its overall process.
And this is also where things get a little dicey with the asset database, because as it's scanning the environment, it's going to pick up a whole bunch of things that are not relevant to this attack, but it should remember those. So if there's an SMTP server somewhere out there listening, we want to keep track of that in a database as well.
Yeah, we can use it later if we want to do phishing in this part of the same operation. Fernando mentioned earlier that SOAR is an interesting language to write. For those of you who are curious, this is SOAR code. This particular SOAR code is designed to deal with the results of scanning a network. A On the left, you see a big XML chunk here. This is one of the goals in that great big goal hierarchy diagram. It's worth pointing out that our goals are data, not code. So adding new behaviors to the agent is a data process, not a coding process. Fernando will talk about why that's important later. Yeah.
Okay. Well, let's talk about what makes our agents effective at representing different kinds of users or different kinds of actors on the internet. We have this concept of a persona file, if you will. A persona is the identity that the agent is going to assume, and depending on the nature of the agent, if it's an attack agent, then this is where we store the TTPs that it knows about, that it prefers. Every actor has a certain set of preferences, whether it's on the defensive side or actually on the offensive side or on the defensive side as well. And it really shines when we're trying to simulate everyday users on a network, because this is where I can model things like I have a particular interest in cute kittens or something, and I have a really positive interaction with Alex, but Alex has not so positive interaction with me. He really doesn't like me all that much. So that kind of nuanced interaction between actors on a network, this is where we're able to capture that information. We discovered, as we were trying to put this together, that our concepts of cyberspace in terms of the persona layer are not all that sophisticated, so we had to do a whole bunch of extra work to catch up. So this is a partial ontology of how we see the interaction between entities at the persona layer of cyberspace. We model this in 3 layers. At the bottom is a physical layer, a logical layer in between, which is really well studied, and then the persona layer, which has a lot of open opportunities for research. And then from that, we then move into the agent itself. So the persona file describes what the agent is going to behave like. We talked so far about implementing these agents in the SOAR cognitive architecture, which is what the attacker and the defender are implemented in. But there's a competing architecture, ACTAR, I mentioned earlier, from Carnegie Mellon University, and this is what we used for the CyCog-U agent. And the reason for that is, if you remember to my earlier statements, the ACTAR architecture is way better at simulating what goes on inside of a person's brain, whereas SOAR shines in terms of external behaviors. So we wanted to intentionally use ACTAR for 2 reasons. One, because we wanted to study human vulnerabilities, the propensity of somebody to do something stupid, and also because we wanted to show that the infrastructure for CyCog, you could plug in different flavors of agents, which brings me to the last category with the Java, and it's just a very, very lightweight agent that we drop in there when we need to scale this thing, and we are okay with approximate behavior somewhere in our network. We don't have to have high fidelity models. And by high fidelity, I mean really high fidelity. I know this is an eye chart, but what I'm trying to show here is something that ACTAR is using called instance-based learning. And the idea is the agent learns by uploading its past behaviors. So in this case, we fed information from an email, from an inbox, a user's inbox, and also from a web proxy. And what we were trying to do was map the user's behavior or likelihood to click on different links. So the agent that we programmed learned that this particular actor, called Alice in this case, has a certain clicking behavior. She only clicks on certain emails under certain conditions. And the agent learned that by just watching the files that we fed it. Then afterwards, through a process of blending, an adversary, it was a human in this instance, was able to walk that actor back through and trick them into clicking on an email that they shouldn't have by retraining it. Much like a user could be duped through an elaborate process of interaction with that person, we can convince them that, hey, this is actually legit, I'm not a robot somewhere out there, which of course we are. But once we get the actor to click, then we need to switch back into the technical guts and figure out how to make the click actually reflect on the real world, on the cyber world.
Okay, so the bottom line here of this little CyCog stack is our abstraction layer. I like to call this our hacker toolkit. It contains a bunch of tooling we use to allow the agents to actually interact with cyberspace. So it's got some offensive tools in it, like Nmap, a PD, and SQL map, and stuff of the sort. It's got some defensive tools like IP table and snort. And then in order to facilitate our users, we also have email reading and web browsing. And there's a handful of other things in it as well. The key breakthrough we figured out to make this work better was, rather than teach all of our agents how to use things like, I'm going to use Nmap as an example here because it has an obscene number of parameters. Rather than teach the agent how to map out all the Nmap parameters and things that it needs to know to run those commands, we taught the agent the concept of an activity, scan the network. So if the agent needs to learn something about a network, it proposes this scan network activity, and we'll parameterize it in some ways. We'll say things like, hey, I need a scan to complete quickly, and I want X, Y, and Z side effects to go with it. It will then send this scan network activity to our abstraction service, and this big long box in the middle, the tool implementation translator, I think we called it here, yeah. We'll find an actual tool, in this case Nmap, capable of making that activity happen. So then this service will assemble an Nmap command with all of the correct parameters that line up with the things to complete the activity, run the command, take the output of it, translate it into such a format that it matches what was originally requested in the activity, and hand it back off to the agent.
Not one-to-one.
Oh, yeah. And the other interesting part about this is the activities and the tools don't map one-to-one. So you might have multiple tools that can fulfill an activity. So for scanning a network, there's many more than one ways to scan a network. So we can put multiple tools out there. And it goes the other way as well. I can have multiple non-related activities that are fulfilled by the same tool. For example, this is a horizontal type port scan, horizontal type network scan. If I want a vertical port scan, I could use the same tool for different activities. It makes it much easier to implement tooling, and it also is worth pointing out that the tools we talk about here are not custom tools we've written for agent. They're standard, off-the-shelf cybersecurity products developed by other people. In this case, they're all open source. All right, so we've given you a bunch of different pieces of this agent. We've given you the riddle architecture for maintaining the goals, the persona layer, the goal graph. Where does it all fit together? So this is Fernando's slightly garish SOAR diagram. When we start the agent up, we load all of the SOAR code, the CyCog representations we need to do the tools, the riddle architecture that's used to maintain the goals, into procedural memory. We take that big goal graph I showed you that had all of the different goal definitions in it, and the parameters for the specific mission we want to work on. We load those into working memory so the agent can reason across them. We take those personas, we stick them into semantic memory as facts. So hey, there's a person called Jack out there, this is his email account, and he uses this service to do this type of thing. And then we take our abstraction service and hook it up to the input and output links so the agent can connect to the world. And when this starts running, you start to see Fernando's autonomy loop of thinking, perceiving, and acting, and then it learns in these memories up here. So that is how it all fits together. From there, we're going to show you how it works.
Okay.
Or at least attempt to.
So one of two things are about to happen. Either this remote demo from Michigan is going to actually work, or it's going to fail and you get to laugh, and then we switch over to video. But we're going to try it because we are brave people and we haven't made any stupid decisions today. Sir, can I ask you for your first name?
Richard.
Richard, okay. Richard, we're going to put your name here just so you see that there's nothing under our sleeves in terms of, this is one of the files that the agent is going to exfiltrate because we are keying in on a key term project Titan. So here we're simulating an attempt to steal files concerning this project from a target system. The mission is already pre-programmed, so the parameters for the mission are already plugged in there. So all we have to do is hit run. And here's
like I said, from Michigan's, we have about a 4-second input delay.
Yeah, so it's going to be a little bit slower than we'd like. But anyway, so here Alex is logging into the IRC channel. I'm sorry, this is the Scram agent logging in and saying, hey, I'm alive, I'm here. And Alex is going to, we really need to use shorter names for these agents. But anyway, Alex is going to say, okay, go ahead and start the mission. So we switch over. Here is the goal graph on the top. As you see, it's starting to populate. The agent knows that its mission is to exfiltrate files with the term Project Titan from a target network that it is given. It also looks through its memory stores and finds that it has email addresses for users in there. In this particular case, only one, and that's for Alice, because we want to keep this contained. So you can see here, actually, you want to take this away?
Sure. So, yeah, my laser thing. Thank you. There's two things that have happened since it started. We gave it a starting goal of possessing information, so it's going to try to take information off of a target network. There are 4 machines you see here up in our VMware sphere. These 3 are on a LAN, and our attacker machine is on a WAN outside of that LAN. When this attacker started up, it decided to possess information off of this LAN network. It proposed a bunch of goals. I'll zoom in on these in a second. One of the things it's done is it's connected to a command and control server for a rat that we're going to infect the local network with, and it sent an email. That email ends up in Alice's inbox. Eventually. And it is an email about cute puppies, and who would ever not click on an email about cute puppies that is supposedly a .m file in Google Drive? It's actually a file hosted on our attacker machine. As I'm sure most of you can guess, it is in fact not a friendly file.
It's a really simple file, just a macro that's going to act as a downloader and install the rat for us.
We open it up, and with this, it should be infected. So the machine we just infected is going to call home to this IRC channel we've logged into. It's on a different channel than this command and control, so you're not going to see its messages. But it is indeed calling home to the same place. We're going to give it just a second here.
Wait for it, wait for it. Or it's going to crash. No.
It says not going to.
So it's important to note that if the phishing attack fails after a certain amount of time, it would try something else.
Actually, it worked. Oh, I thought we had timed out. That's lovely. So you can not read any of this. I promised I would show it to you big enough that we could show there's nothing up our sleeves.
So the agent is doing multiple things at this point. If you saw the rat connect already, let's key in on the blue little bubbles at the bottom. The second bubble is a rat scan. So the rat is scanning the local environment for SMB services because it's going to use Eternal Blue to do lateral movement. And then on the if you scroll to the right, we have the agent is also going to be looking through the local file system of that first computer. Oh, look at that! Switch the video. So the agent is also going to look to a VPN from here to Michigan. It's just not, it wasn't smart, but hey, go ahead and laugh. I gave you license. So this is the exact same video. We just recorded it beforehand just in case something like this happened. And on the far right-hand side, you're going to see that as the agent is scanning the local network, or the rat is scanning the local network, it's also looking in the local file system for files that have the string Project Titan. It's going to find them, and then eventually it's going to. Oops, I'm ahead of the video. Can you fast forward a little bit, please?
No.
Okay, we get to do this slower.
There we go.
All right, so it's going to be looking in a local file system, and then when it finds them, it's going to exfiltrate them in a really stupid way because we didn't have to get fancy on this thing. So it's just going to, as soon as it finds a file, it's going to upload it to an HTTP server that's running on the attacker's box. We can try this in any number of complex ways. We just wanted to keep it simple for the demo, trying to optimize our odds of it working. Almost there. And over time, it's going to find 2 other hosts that have SMB, 2 other Windows boxes. We showed them earlier, Carol and Grace, and it's going to infect them and then install rats, and the rats are going to phone home, and then a grand total of, I think, 4 or 5 files are going to be exfiltrated at the end of the day. And why don't you fast forward to the end?
The end of the video isn't as lovely because it shows me pulling up a copy of the file I placed in the beginning of the video, which we didn't show. I'm going to take one more gamble here, and despite the fact that our GUI crashed, I'm pretty sure the attack will have finished, and I should be able to show you that file has exfiltrated.
So a couple key takeaways here. The first one is that the agent is given some very, very broad broad goals. It says, go do this, and it searches through its knowledge of TTPs and figures out what is the best way to get from here to there. As it tries and fails different approaches, it can learn from the experience and say, okay, against this particular target, I tried this and it didn't work before. So next time I'm not going to try the same technique again. In the interest of time, you want to go over to back to the slides?
Yep.
So if you caught that at the tail end of the video, we showed how we actually went in and opened up those files in different folders in the web server. The reason we do that is we want to be able to keep track of where we got each file from, so we can capture some metadata about users and locations and anything else we want to along the way. So moving on to future work, I want to key in on 3 things that we discovered that were a lot harder than we thought going into this, and that we have to circle back and put some more effort into. So it's keeping track of cyber stuff, and we kind of alluded to that already. The second one is modeling TTPs in a formal way, and then lastly, the human-machine teaming aspect of the whole enterprise. So keeping track of cyber stuffs, as we alluded to earlier, is really, really hard. Actually, another client came to us and asked us to help them build models of cyberspace in these 3 layers. And this is actually where a lot of the work came in analyzing the work that had been done already at the persona layer analysis. But what we have here is that it's not just about cybersecurity. We can learn all kinds of interesting things about what's going on in a network. Some of the scenarios we came up with involve people doing strange things that need explanation and that could have a detrimental effect on our security posture. So this was hard. The second piece was building models of TTPs. I mentioned earlier that non-symbolic AI, machine learning, is really, really, really good at classification problems and that sort of thing. Not so good at the complex behaviors that we implemented here using the symbolic approach. But it turns out that if we are able to have models that can be shared between the two, we could detect TTPs using non-symbolic approaches and actually input them into a symbolic system that can either defend or then use those to learn what targets are hitting or what attacks are threatening a particular environment, and then do targeted pen testing in real time. This is to show that our approach to building TTPs is not built in isolation. So this is actually an overlay of the MITRE ATT&CK framework on top of the TTPs that we modeled for APT28 and the Pawn Storm campaign that was well documented years ago. So these are techniques out of the attack framework. Going back one slide, those that then further decompose into procedures, and procedures is really the glue that ties the whole thing together. At the very bottom, we have observables, things that you can see on your network, like IP addresses and domain names and malware signatures and whatever you have. And then at the top, we have these higher concept kind of techniques. So the procedures are the things that tie the two together and say, this particular adversary uses these procedures if they're going to do this thing, they always do it this way. And there are variants of it, and those variances is what we capture inside of the body of one of our techniques. And this allows us to map out who might be acting on our network and also what their goals ultimately might be, which gives us a heads up in terms of intersecting that. Now, putting the whole thing together, if we can build, as we develop these models, the TTP models, we wrote a paper last year, so we're hoping to get the whole community energized in it. We're also talking to Palo Alto Networks. Rick Howard has a great project on playbooks and adversarial playbooks that also leverage the MITRE framework, but are still not robust enough for for artificial intelligence to really do much with. So this is where we're hoping to tie into that effort. So we classify procedures from observables, and then from there we build techniques. And then because there's so much variance in there, we use abductive reasoning to come up with the best explanation for the observations that we're seeing on the network. And then this brings us to the last piece, which is the human-machine symbiosis. Because everything on the left is symbolic and non-symbolic AI symbiosis. So leveraging the strengths to offset the weaknesses of each approach with the other. But on the far right, we need a human to be part of the system, and how do we manage that relationship and how do we build trust is something we're very active in. Things like how can a human teach an AI system how to learn experientially by watching what the human does, and then how can we then take the CyCog agent and have it teach a novice human how to do things in cyberspace. And that's it in a nutshell. So hopefully you have lots of questions, and then we can continue the conversation. Thank you very much for your time.
Right. Thank you for a very cool talk. Stupid question. So you said that you started with CyCog-A and then you shifted to the CyCog-U. Can you explain a bit what you plan to do with those, let's say, random citizens in longer term, besides, I don't know, testing their capacity to resist phishing or?
Okay, right. So if I understand the question correctly, is what is the relationship between CyCog-A and CyCog-U? The whole purpose of building CyCog-U was we wanted to identify human vulnerabilities, right? So when would people click? But that's a simple example. It's actually much broader than that. CyCog-A was used to do the testing. So we would build an environment with CyCog-Us, and then we could launch CyCog-A against it many times, and then record results and see how effective the model that we derived from a particular population, how effective was a particular attack against it. Does that answer your question? No, I missed the mark. Okay.
So the other fun thing you can do with these agents is, as cybersecurity grows and we need to train more professionals, one of the common things we do is we build cyber ranges for people to actually experiment on and test. If you've ever worked on those ranges, experienced people frequently will sit down. The first thing they'll do is take a look at all the traffic they can see and immediately parse out, oh, that's generated, that's generated, that's generated. Oh, that's real. I bet that's what's the interesting part. Well, if we can take cognitive agents that are having conversations over email that look somewhat realistic, at least at a cursory glance, and then put some attackers in this network and put some defenders on it, and then throw a human in, all of a sudden, one person sitting by themselves on a cyber range can work in a very lively, realistic-looking environment.
So we don't build products, we just kind of build smarts that go into products. And this is the conversation we're having with a commercial transition partner, is how we then use this for improving the quality of training events.
I think it's opening.
My question is kind of more about, so you create these kind of agents who are sending out phishing and doing all sorts. How do you establish the trust apart from saying they like adorable puppies, they're selling adorable puppies? Because surely, who are they sending it from, if that makes sense? Because if you've popped up a new person on the internet, how do you not look at that and think, who is this person? They've got no social media, nothing, it must be a hoax sort of thing. Can you look into any of that?
Great question. So we are not in the business of creating fake social media personas out there. Let me put that on the record real quick. If you think back to the IBO, the instance-based learning example I showed up, that complicated chart with lots of equations, it was actually, it went way beyond just cute puppies, click on the link. It exploited the relationships between Alice and some of her co-workers. And so the agent learned the model of those interactions by observing the environment and then sent very targeted links. It figured out that Alice was only likely to click a link that, without questioning it basically, that came from a very particular class of users. And if she saw that, then she'd be more relaxed and she would click on the link. And that's what the attacker exploited. Does that answer your question? Okay. Wonderful.
I don't know if anyone noticed it, but the exfiltrated file did actually show up, despite the fact that we never confirmed it. And it's super tiny in the corner, and I have no idea how to zoom in on this text editor.
Anything else? Oh, you're letting us off easy.
Did you learn any interesting vulnerabilities about yourself? You did test this against yourself?
I'm sorry, one more time?
Did you learn any interesting vulnerabilities about yourself?
So I'm fairly certain our IT team would have my head if I actually ran this against our local production environment. So I have not done that. I can share one slightly amusing story, though. That rat in there is a Java rat, and it does have some tooling in it. And one of our concerns for a while was we wanted to make sure people developing it weren't running it locally. And after working on it for a couple of weeks, I ran the IRC lookup against it and found that it was running in a significant portion of the machines in our business area of our company. It hides itself fairly well, and it worked.
And of course, now we're on video admitting that, so we may be handing out resumes later.
Yes, thank you. Forgive me if this is an unimportant or a stupid question, but is it fair to say, are you able to say anything about the relative role of a human in all this? Will the human analyst that you had at the end, will that diminish over time, or is it just impossible to say?
Oh God, no. So my personal perspective on this is we need autonomous agents to speed up the process and to bring to the humans the things that they should be paying attention to. Right now, I'm sure most of you would agree that we have an awful lot of brilliant cybersecurity experts out there wasting their lives away looking at stupid stuff. So the idea is to focus these very valuable human assets and enhance their performance. The adversaries are going to be using intelligent agents at some point. My guess is sometime in the next couple of years. So we need to do that just to keep up with the pace or the speed of these attacks. But no, our work is we're trying to move humans from being in the loop to being on the loop, and then that's where that human-machine symbiosis comes in. Is how do we manage that relationship between the two? No, one more. 5 minutes left. You know, this is amazing. We kept going over and over and over every time we rehearsed.
All right.
Please.
So I'm curious on your perspective on all the work you do using this framework, is it more advantageous for offense or defense? Because it seems like the feedback cycle for offense is faster. You know if you get the shell, you know if the link is clicked on. But for defense, you're unsure necessarily what was the thing that actually protected you. And so I've been thinking that probably initially all these tools will be more effective for attackers, and the defenders will be in more trouble until they can catch up. But what do the experts think?
You want this? So they're very different problems. The attacking problem is much more of an exploration problem. We wander into an environment, we start off with some targeting reticle, and we try to discover more and more things we can do as we progress through compromising a network. Whereas defenses, we start out with everything we can do and then try to stop that attacker from exploring our space. They're really different problems, and like we said, we're not trying to replace humans. I don't think either of us believe that we're going to pull humans out of the loop. This is human on the loop. And like that defensive agent, in the screenshot example I showed, it detects something that it identifies as not critical to the infrastructure and really unexpected, and it immediately creates a firewall rule, and then it tells the person, hey, I did this action to block this thing. So reaction time is one. We get a ton of reaction time out of it. And two, if things do go haywire, it's like having extra people in the room. So I wouldn't expect this anytime soon to replace your senior guys, but replacing your junior guys, I could very much so see happening in the next few years.
So different perspective on the answer is it going to be more advantageous for the offense or the defense, at least initially? Keep in mind that what I'm concerned about is that that non-symbolic AI is going to be used soon to make attacks quicker and harder to detect. That's already happening in some of the systems I showed up there. So what we're trying to do is kind of prep for that by building these agents that can respond at machine speed to these attacks. along the way, we hope to develop the CyCog-A agent to anticipate what some of these non-symbolic approaches are going to be and how humans might help them. And where CyCog-A would shine is that allowing us to do these attacks many, many times in experiments and see, oh, that's how we break those attacks, or that's how we detect them, or that's how effective our defenses are. Some of the interest that there's some agencies that are very interested in our work because they want to use it to test new capabilities. Like you roll out, you sell me a brand new firewall. Let me see how well this stacks up against the attacks that I'm facing. So this is all. Everything we show you today, I think, has very strong defensive implications. Could an attacker use these techniques? Not anytime soon. It took us a while to get here, and hopefully we don't get hacked as a result of this and lose it all, but that's okay. Does that answer your question? Okay. Oh, our time.
Oh.
Okay. Well, we're here for a while, so please hit us up. Thank you so much for your time and your questions.